3 years. I'm very grateful to my supervisor of my postdoc, Sophia, who's allowed me to work on this fascinating problem with Jonathan, Jeffrey, and Rick, who are all oceanographers, but sort of very mathematically minded ones, who it's been really great to apply modern time series techniques to oceanographic problems. And it's not just about application. We've had to build new methodology as well, because the data has this interesting nature to it, as you shall see. So we've had to develop some new methodology. I can't present it all, but I'll give hopefully an overview in my 20 minutes. So I'm going to jump straight in and show you the data. Here's a map. It might be a bit weird to understand straight away, but what this is the Global Drifter Program. It's a collection of floating, freely drifting devices. They're maybe about twice the size of a basketball, and the idea is that they're deployed and they freely drift on the surface. They sort of wiggle around, and they communicate their position and other statistics such as water temperature and salinity to satellites that orbit around. And we're specifically interested in the positions. Because what they give you is this sort of map of how the surface of the ocean, how it moves, how it circulates. In total, there are over 10,000 drifters. The data goes back to 1979. So we've got over 13 million data points overall, so it's kind of a big data type problem. And why do people care about this data? What's it used for? Well, it's used for many things. One thing in particular is climate change. So climate change that occurs over decades or centuries, it's becoming accepted that this is primarily driven by our oceans. So from this data, we can get an understanding of how perhaps these things are related. So findings from this kind of data will feed into global climate models, for example. But there are other applications as well, such as how we might respond to oil spills. We get an idea of how things might sort of diffuse and spread as well from data like this. And our sort of objective isn't going to be forecasting, it's going to be summary statistics. And I think the general feeling in the oceanographic community is that we haven't got as much out of this data as we could. Lots has been done, people do some neat things, but maybe a modern time series approach where we build really nice models could potentially extract something more out of this data. So with these applications I've talked about, we can make bigger advantages, richer conclusions. But it's a tricky statistical problem because each one of these squiggles shows you where one drifter has gone. But this is a very inhomogeneous problem. They're distributed unevenly. They move differently in different parts of the ocean. So it's a statistical challenge as well. So let's strip it back, look at just one drifter. This is one from the North Atlantic. It starts at the bottom here, and it follows this trajectory. It goes in and does some crazy stuff there in the top, and then comes out. And there's a lot of rotations here. Some of these oscillations, you see some are clockwise, some are anti-clockwise. And what we're going to do is model this as time series. So you're going to take a position. This is called a Lagrangian trajectory, but we're going to turn this trajectory into a time series, specifically a complex valued time series, which we're going to call ZT. And X, it's going to be its longitudinal position at time t, and Y, its latitudinal position. And it's sampled. So that's why we get a time series. It's sampled from satellites. So we have a time series here, and we're going to look at the velocities. So if we know its positions, we can difference the positions to get an idea of the velocity. What's its speed in the latitudinal and longitudinal direction? The reason for representing this as complex valued is several-fold. First of all, it's computationally and mathematically convenient. But also, when we're talking about rotations, oscillations that are clockwise or anti-clockwise, this is a very powerful way of capturing these, and we can build models specifically that are for complex valued processes and inference procedures as well, which might be much more complicated, harder to interpret if we were looking at bivariate time series. So let's start looking at the non-stationary nature of this data. So this is a different drifter now from the South Pacific. Perhaps I can start convincing you, then we have global coverage. What you see here is a spectrogram. And so what that means is the bottom axis going along here is days. So this is time. And then the y-axis is frequency. This is time frequency plot. And the color intensity is going to be the energy in, this is a periodogram, so it's the energy in the power spectrum of the velocity time series. And what we should notice here, the frequencies go from here from 1 to -1 in radians. And it's asymmetric if you look at 0 and what's above and below. And that's because with complex valued time series, unlike real valued ones, you'll have asymmetry in the power spectrum. This is because things that are rotating one way, clockwise or anti-clockwise, will live on different sides of the spectrum. So in this case, we have this band of energy here, which is positive frequency, so it's an anti-clockwise rotation. And these are spins that occur because of the Coriolis effect. So this is the fact that the Earth is spinning on its own axis, and it creates an oscillation in the drifters. And we observe this in the power spectrum. And that's this band of energy here. And notice the sort of non-stationary nature. The drifter's moving, so the frequency changes at different latitudes, and that creates this non-stationarity. And also we have this band of energy at 0 frequency, which is called sort of the background red process, which is effect of turbulent flow in the water. I don't want to go into an oceanography too much, but we've sort of got two key bands of energy that we observe in this data. And what we're going to try and do is we're going to model this. So we're going to model this as two stochastic processes, one for each band. And first we're going to model this as a locally stationary process. So we're sort of going to zoom in, shrink this down, and say it's stationary. And I think this sort of looks like, locally stationary modeling could work. That it's a continuous process. We won't get huge jumps ever in how things change. So we're going to go with the locally stationary approach. And the idea is we're going to combine two stochastic processes for those two bands. So one for each band. The high frequency oscillations, that's the Coriolis effect. We're going to model this as simply a complex valued OU process, Ornstein-Uhlenbeck process. So what that is, the complex valued one, it's the real valued one plus an additional parameter which creates a spin. It's a spin parameter, creates an oscillation, which can be in whichever direction the value of that parameter is. And then you've got the usual forcing and damping term that you'd have in a real valued OU process. And then the second background process we're going to model as something called the Matern process, also a 3-parameter process, again forcing and damping, and a third parameter which defines the smoothness or differentiability of the process. It's kind of how rough it is. And both of these processes, I don't have too much time today, picked using evidence from the data and also looking at the kind of applied maths modeling you get in fluid dynamics, and picking processes that can kind of summarize in a few parameters what the applied maths understanding is of how these processes change. They're simplifications, but the reason why we want to be quite simple is that now we have a 6-parameter model, and if we have few parameters, that's very useful for a locally stationary model because we can zoom in and estimate those parameters from short data, from short time series, which is good for resolving the non-stationarity. So if we add these two together and look at the power spectrum, then it follows this simple form in the frequency domain, where this is the spectrum of a complex OU, and this is the spectrum of a Matern, where this delta is this smoothness parameter, so it defines sort of how jiggity the trajectory of the drifter is. And yeah, I refer to this preprint submitted last year if you want more details on how and why we selected this model. And then before I show you it applied to the data, a quick note on some of the methodological advances we've had to make in order to be able to estimate parameters from this model. There have been a number of challenges. In the base case, if we've defined a model in the spectral domain, we can use the Whittle likelihood, which is a frequency domain form of maximum likelihood given by this equation. And the idea is we have a ratio of the estimated spectrum to the true spectrum plus log of the true spectrum, and we sum over frequencies, omega. And then we maximize this with respect to our parameter vector theta, our 6-parameter model. And in the spectral domain, it's preferable, at least asymptotically certainly, to other spectral estimators such as least squares. And it's because of, covered in the last talk, we can use FFT. We've got the computational benefits, and we can now do things in order n log n, rather than having to worry about inverting covariance matrices, which is order n cubed or n squared if they're toplets or whatever. But there's a nice computational convenience there. But there are still problems, and these are problems we've had to overcome. One of which is that the reporting of drifter positions will be irregular in time. The data will be irregularly sampled. And that's because they move. The satellite orbits are regular, but if they move, then they're going to be at the gaps between observations will change, and also there are multiple satellites. So sometimes it'll be picked up by one, but then it'll move and be picked up by another. So what they usually do is interpolate this data onto a regular grid. So usually when we get the data, it's already interpolated. But that can lead to problems when you have interpolated data, because if you take the Fourier transform periodogram, you look at the spectrum, you'll notice that this can tamper with the high frequencies especially quite a lot. And it depends on what, if you change the interpolation method, you might get a different looking spectrum at high frequencies. So do we really want to be modeling what we don't know? And there are other issues such as rounding and measurement uncertainty. So what we do, quite simply, is we take the Whittle likelihood, and now we sum over a reduced set of frequencies, omega in capital omega, and we cut out these high frequencies due to these sampling effects. And in that way, we're sort of being semi-parametric, because we're saying we're not modeling that high frequency range because we're not really sure about this interpolation problem. And also we have the advantage that we can only use one side of the spectrum, so we can just model negative rotations or positive rotations, particularly because we're often interested in this Coriolis effect, so we might just look at that side of the spectrum and ignore the other side. And that allows us to ignore any possible correlations between positive and negative. This will occur, some technical jargon, when the complex value time series is improper, such that it's sort of no longer circular looking, but more elliptical looking. But we sort of don't have to worry about these things if we just look at one side of the spectrum only, and we can still fit our model to the data. There are still a few problems, because actually we're using the periodogram. And as many people will know, the periodogram, which comes from the discrete Fourier transform, absolute value squared, its expectation is not equal to the true spectrum. So if we're going to use the periodogram, then this can lead to badly biased parameter estimates because of phenomena such as aliasing and leakage. And especially because we're going to be using short time series in our locally stationary windows, we're particularly concerned by these sorts of effects. So we don't want to be worried about bias in our parameter estimates. So what can we do? Sometimes people will use tapering for aliasing. They'll use summations to fold in frequencies higher than the Nyquist. But we can actually avoid these sorts of summations and tapering by making use of the fact that we actually have a model. We know the autocovariance sequence. So we can look at the expected value of the periodogram, which is that first object there, and say that actually it forms a Fourier pair with the biased sample autocovariance sequence. So, okay, so we know that, but actually we know this bias. We know this bias is a function of the lag. It's this sort of triangle kernel, and we know the autocovariance sequence. So now we know that the expected value of the periodogram is the Fourier transform of the autocovariance sequence multiplied by this triangle kernel. So why not just use this in our Whittle likelihood? So what we do with the Whittle likelihood is we replace the true spectrum with the expected value of the periodogram in these two positions by using this relationship in the top equation. And in another preprint from last year, here we argue on theoretical grounds and using simulations that this leads to better results and removes the bias caused by aliasing and leakage, as opposed to traditional Whittle likelihood where you'd use the true spectrum there. So it's an adjustment which, for small samples especially, creates significantly reduced bias and variance in our parameter estimates. There's still the issue of correlation between frequencies, but we show in our paper, again, theoretical grounds and simulation, that that's less important. The bias problem was the big problem, and this adjustment, this methodological adjustment, allows us to deal with bias issues from small sample time series. And this is what the fit looks like for zooming in on a locally stationary window. So we're semi-parametric in frequency because we just model the green range in the power spectrum. So we've got the two peaks. One is the background, the other is the Coriolis effect. And with 6 parameters, we've captured the energy in this frequency band. And extending it out to other frequencies, the fit is generally good except at high frequencies where you have the issues with interpolation, rounding, and uncertainty, which haven't affected our parameter estimates because simply we've been semi-parametric and not included them in our maximum likelihood. So I'm going to skip, quickly talk about this slide. I only have a couple of minutes left. So really we're talking about the non-stationary problem. The data I showed you earlier was changing all the time. So in our stochastic model, we make the parameters time varying. And then using the type of ideas discussed by Rainer Dahlhaus, we extend these to complex valued data by using these sliding windows over the data. And this is, again, another semi-parametric approach. We have a parametric model for the drifter data in the locally stationary window, but the evolution of the time-varying parameters has no model in itself. So that part is not parametric. So overall, we have a semi-parametric model, and we do semi-parametric inference. Of course, setting the right window length is non-trivial, but I don't have time, so I won't discuss that further. And I'm going to skip ahead straight to my final slide of simulation results. So I've got a video as well I want to show very quickly. Here we have the spectrogram of some real data from the North Atlantic drifter, where this is the low frequency energy and the high frequency energies on top. And this is what we get from our model. So it's sort of using these rolling locally stationary windows. What we get is we capture the various high energy areas and the non-stationarity over time on this axis. And then if I turn, it's a non-stationary problem, so great to watch as a video. Here on the left, we see the drifter moving and following this trajectory. It's about to enter this highly oscillatory motion here. And what happens here is we see that using these rolling windows, this is the periodogram, and our green semi-parametric model fit to this data and how it's moving and adjusting as the sliding windows move forward in time. And what we see is that the frequency of the Coriolis is actually going to move away from what the physicists expect, which is a phenomenon of what happens when it enters this circular region called an eddy. Don't worry about the oceanography too much, but what you can see is how our model can cope with this. So the green peak on the left is moving away from the red line, and with our models we can detect these sorts of regions, and we can give these figures, the parameter values, back to oceanographers who find it useful because they can detect regions where there are interesting things happening. And here we sort of see it leave the eddy and return to sort of normal type motion where the green peak goes back to the red line and you have the nice fit over all frequencies. And we just modeled this narrow frequency band in order to be able to estimate all 6 parameters in a time-varying fashion. And I think I'm out of time, so yeah, I'll finish there with this running in the background.
So you've got 10,000 of these drifters all moving around the ocean at the same time. How do you combine the information from lots of them together into one?
Yeah, so that's bang on what the future work is. So this is a single drifter analysis, and at the moment what we have is time series. What we then need to do is translate this back into the spatial domain. So this drift is moving, we're getting some information about its characteristics, and then we put it back in the spatial domain and look at other drifters that are going through the same regions, and we compare those parameter estimates. So we might say, oh, the damping parameter of this process is this value for this drifter. What about other drifters that have gone through the same region? Do they have similar kinds of damping parameters? And we can aggregate those statistics and start getting spatial maps of how the ocean is varying across different oceans and across longer scale time as well.
I thought it was nice using the complex process. But what would you do if you had three-dimensional spatial data for something that wasn't a drifter? Is there some other convenient formulation you could?
Yeah, I mean, they do have obviously the third dimension, which would be the depth.
Yeah.
So there you might look to try and model a 3D process somehow. But typically, I think with the ocean and water, they sort of have these layers that sort of move on top of each other. So you might look to model them both as complex valued processes and look at how they are correlated with each other. But I don't know to be honest, I don't know.
Quick follow-up to the first question. With 10,000 of these things out and around, what would be a typical range of distance between them at any one time? How close together might they get? How far apart might they drift?
I mean, they're not in any way controlled. They're sort of free. They're freely drifting, and obviously the ocean's big and they're small, so they don't hit each other or anything. But actually, when they are very close to each other, that's actually very useful to oceanographers, because that allows them to then determine what is a first order mean flow, as they call it, and what's second order dispersion, because they can look at the relative difference between how they move and separate first and second order properties.
Do they get close together very often?
No, not so often.
Thank you.
Yeah, how do you actually minimize that with some lighting?
In MATLAB, actually. So, you can just use, it's using fmin search type stuff, because it's all n log n. And the adjustment we made didn't lose the n log n-ness. The adjusted Whittle likelihood we used to account for finite sample issues, it's all n log n. And for sort of this, for one drifter, it might take on my laptop, a couple of hours to process the whole thing. So with 10,000, with some parallel computing, you can do it the whole lot over a week or a weekend. So it's not so bad.
Maybe you should say that you spent some time having good starting conditions.
Yeah, good starting conditions. Good starting conditions help, but actually with rolling windows it's easy because you do a fit, you move the window one across and you can start with the previous.
You do hot restarts, yeah.
Yeah, exactly. Yeah.
So, is there an interest in finding boundaries for these regions? And
Yeah.
you haven't touched on it here, are you?
Yeah.
Doing that? Yeah.
Yeah, absolutely. So actually, there's the sort of obvious boundaries like a coast, but actually there are other boundaries which you wouldn't be able to see, which are to do with ocean depth. So actually, if the ocean depth changes, generally these drifters will go along them and not across such contours. So it creates anisotropic data. And some of the methodology and models we've built, which I haven't been able to show today, allow us to deal with anisotropic flow. So something that's more one-directional. Here, this is assumed to be what we call a proper or a circular process.
From the oceanographer's perspective, are they interested in identifying those
Yes.
boundaries or changes or edges?
Very much so, yeah. So that's one of the applications we're looking to build on.
Yeah, I really like this trick of adjusting for the bias in the periodigram, but why has that not been done before? Because the bias has been known always, more or less, hasn't it?
Yeah, I guess maybe there hasn't been so much spectral domain research using parametric models. Maybe people who do spectral domains often do it with non-parametric.
But Whittle likely parametric.
Yeah, exactly. Yeah. So I don't know why it's not been done before, but we found it made a significant. It's actually computationally faster, and it leads to reduced bias and variance.
And you reckon that the trade-off between, does it give you extra correlation between the frequency bins?
It doesn't give you extra correlation, no. It doesn't kill it, but the bias issue is worse than the correlation.
Yeah.
That's all, right? So this was the last talk of this session and the last talk of this day. Let's thank all our speakers, Francesca, Max and Adam, again.